Welcome, general chemistry students, to the fourth video in week 10. In this video, we're going to be looking at determining the rate laws based on experimental data. So we're going to use that experimental data to determine our rate equations. So at the end of this video, we'll be able to calculate rate constants given concentration data and determining the rate law based on that data. And so this is a rather difficult concept, and so it may take some practice on your own by and how to determine finding these rate equations based on experimental data. So you might have to dig a little deeper on your own to come up with these rate laws. Okay, so I want to start with an example. Okay, so in this example, the rate equation for the reaction of NO with ozone is as follows. We have rate is equal to our rate constant times the concentration of NO times the concentration of ozone. And so what we can say here, just looking at the rate law, is that the rate is first order with respect to NO, and first order with respect to O3, and second order overall. So if we know the rate of reaction is 6.6 times 10 to the minus 5, when the concentration of NO is given and the O3 is given, we're going to calculate the rate constant. All right, so what do we know? We know the concentrations of NO, we know the concentrations of the ozone. We know the rate at that concentration. What are we going to do? We're going to find the rate constant. And this is a second order rate reaction, and so the units for the rate constant are per molar per second. All right, so essentially what we're going to do is we're going to take our rate and our concentrations and turn that into a rate constant. We know the relationship based on the rate law. Okay, so now what we really have to do is just plug in those numbers to find out what the rate constant is. Right, so we will take our rate that's given in the problem and divide by our concentration of NO times our concentration of O3. And when we solve that out, we get 2.2 times 10 to the 7th per molar per second. Okay, so this is the units for a second order reaction, per molar per second. Because if we look at solving for the rate constant here, our molars cancel out to give us per molar, and you can see here per second. So that's the units of a second order rate constant. Okay, so let's practice again. So we have a rate law for the decomposition of acetaldehyde, right? And it says that it's second order with respect to the acetaldehyde. What is the rate of the reaction when the acetaldehyde is equal to 1.75 times 10 to the minus 3. All right, and here we're given our rate constant. Okay, so we just have to solve for the rate given our concentration and given our rate constant. Okay, so let's think about what we have. We have our concentration of acetaldehyde and we have our rate constant. What we want to find then is the rate in terms of molar per second. So we're just going to turn those two things into a rate, given our rate law. Okay, so we find our rate by taking the rate constant that we're given times our concentration squared. Now, don't forget about this part. This is really important. It's second order with respect to acetaldehyde. That means we have to square that concentration. So here the rate is 2.06 times 10 to the minus 11 molar per second. So that's the rate of that reaction. All right, so now let's think about how do we use experimental data to find a rate law. So importantly, the rate law has to be determined experimentally. You have to do the experiment in order to know the rate law. And so we're going to use the method of initial rates. And the method of initial rates is when we look at the rate of a reaction at the beginning of a reaction, right? So the initial rate of reaction is what we're going to use to determine our rate laws. Okay, so here we have a reaction where we have some A going to products. So we have a concentration of A in molar, and we have at different concentrations, and at different concentrations we have the rate that we measure. Okay, so let's think about what's happening here. We're going to double the initial concentration of A, and what happens to the rate? Well, here the rate does not change, all right? Doubling the concentration, the rate does not change. So what does that mean? All right, and then let's look at this one. So here we have A going to products. We're going to double the concentration, or sorry, quadruple the concentration, double the concentration, which quadruples the rate. Right, so what does that mean? Okay, so for the first reaction, we found that the reaction was zero order. Okay, and so the reason we say it's zero order is because doubling the concentration of A had no effect on the reaction rate. It had no effect on the reaction rate. So N equals 0 here. Okay, so that means it's zero order. In the second reaction, doubling the concentration of A doubled the rate of reaction. All right, so double, all right, and so that means it's first order, where N here equals 1. All right, so our exponent there is equal to 1. That's first order. All right, so imagine a situation where if a reaction is second order. So here the rate is going to be proportional to the square of the reactant. So doubling the concentration of A will quadruple the rate of the reaction. So N is equal to 2. Okay, so we're using how changing concentration affects the rate. That's how we're getting these rate laws, and particularly that's where we're getting those exponents. All right, so how do you determine a rate law if there are multiple reactants? Okay, so this is where you have to really plan your experiment. You're going to have to change concentration of each reactant individually, because changing each reactant will affect the overall rate of reaction. And so if you don't want to get confused, you always have to hold one constant and change the other, and then go back, hold that one constant and change the other. So you only change one thing at a time to determine how the concentration of that particular reactant is affecting the rate of reaction. Okay, so imagine this reaction. So we're going to determine the rate law and the rate constant for this reaction. So we have NO2 plus CO gives us NO plus CO2. We did 4 experiments. And in these 4 experiments, we changed the concentration of our reactants and we measured our rates. Okay, and so in the end, we're going to come up with something that looks like this. We have rate is equal to our rate constant times the concentration of N2 to the nth power. That's what we're finding is N, and times CO to the m power. Again, we're going to find that exponent also. Okay, so we're going to examine the data and find 2 experiments in which the concentration of one reactant changes but the other doesn't. Right, so if we look at this, we can see in experiment 1 and 2, we are doubling NO2. Right, we're doubling NO2. The rate then is quadrupled. All right, if we look at 2 and 3, we are doubling CO, and the rate really doesn't change. Okay, so let's think back to what that means. All right, so comparing experiment 1 and 2, we find that the NO2 changes, but CO does not, so we can look at the effect on the rate. And so what we see is, well, we're doubling NO2, and the rate is increasing by 4. Okay, and so that means then, so we're doubling, that's 2. So 2 to the n equals 4. So n here equals 2. So we can say that the rate is proportional, right, is proportional to NO2 squared. All right, that's all we can say with those two experiments because we kept the concentration of CO constant. All right, so then let's go over to the next one. So if we look at reaction or experiment number 2 and 3, here NO2 stays constant, but we're doubling CO. Well, what happens to the rate? Well, it's essentially the same, right? It doesn't change. Okay, so what does that mean? Well, we're saying here that 2 to the m equals 1, and so then m must be 0. And so we can look at the rate relationship and say that rate is proportional to CO to the 0 power. Okay, so it is 0 order with respect to CO. All right, so let's bring that all together. We have n equals to 2 and m equal to 0. So now we can write out the rate law based on the data that we see. So the rate here is equal to K, the rate constant, times NO2 to the 2nd power, because it's 2nd order with respect to NO2. All right, so now the next step is, now we want to solve for the rate constant. So we have the rate law. We can use the concentrations from the experiments and determine what the rate constant is. Okay, so remember that the rate is equal to K times NO2 squared. So we can say 0.0021 is equal to 0.10 squared times K. All right, and if we take our calculators out, we can see 0.0021 divided by 0.1 squared, and we get 0.21. All right, and remember, for our 2nd order rate constant, our units are in per molar per second. Okay, so that's our rate constant. All right, so let's do one more here. So we're given this data. We have four experiments, and we have 2 reactants that we need to look at. Okay, so we can formulate an initial rate law where we raise the concentration of ammonia to the N power and the concentration of nitrite to the M power. Okay, so let's look at experiment 1 and 2. Okay, so in experiment 1 and 2, we're going to triple the concentration of ammonia and leave the concentration of nitrite the same. So we're going to triple it, and then the rate for experiment 2 and 1 is tripled. So that means that 3 to the n equals 3. So here we can say n equals 1 for the concentration of ammonium ion. Okay, so now we want to do that for nitrite too. So let's look at nitrite. We're going to look at experiments 3 and 4. Here the concentration of ammonia is constant, and so we're just changing the concentration of nitrite. And when we change the concentration of nitrite, we're going to double it. So the concentration is up by a factor of 2. We look at the differences in the rate. So we take the experiment 4 rate divided by the experiment 3 rate, and we get 2. So what we're saying then is 2 to the m equals 2, or first order. Okay, so now what we can do is write that rate law again. All right, so let's write the rate law. So here we can say the rate is equal to the rate constant times the concentration of ammonium ion to the first power times the concentration of NO2 to the first power. Okay, and if we just plug in the numbers from experiment 1, we use the initial rate is equal to K times the concentration of ammonium ion times the concentration of nitrite, and we get K. And remember, this reaction is second order overall, so our units here are in per molar per second. All right, so that is the end of video 4 in week 10 on determining the rate laws based on experimental data. Thank you.